Hi everyone, here's our experiment 8, which is called Aldol or Claisen-Schmidt condensation. Okay, you are familiar with Aldol reaction and condensation, but let's see what is Claisen-Schmidt condensation. Okay, so the purpose of our experiment today is to carry out a condensation reaction using ketones with aromatic aldehydes. Now, what is the meaning of aromatic? Aromatic means, of course, aromatic compounds have a nice aroma, but here the meaning of aromatic is it contains a benzene ring. Okay, and we're gonna characterize the product by measuring the melting point. So your learning objective for this experiment is to perform that condensation reaction with aldehyde and ketone. Okay, and then the other stuff we have talked about earlier to form a precipitate, and then do a vacuum filtration, determine the melting point, and also finding out a suitable solvent to do a recrystallization. Maybe we do not do the recrystallization, but we'll see. So background and discussion, you guys know what is an aldol condensation. We learned about that in our lecture. It is a reaction where you have a enol and then it forms a enolate ion in the presence of a base, and then it's going to react with the carbonyl compound to form a beta hydroxyaldehyde or a beta hydroxy ketone. And we name this product as an aldol product. Aldol means it has an aldehyde and an alcohol. Okay, so once the aldol is being formed, we know that the alcohol, the OH group, can be dehydrated, meaning removal of a water molecule, give you a alpha beta unsaturated aldehydo-ketone. Okay, so you can have a alpha beta unsaturated aldehyde or a ketone. When this is the result, then we call overall reaction as an aldol condensation. So the meaning of the name condensation is when you put two molecules together, it forms a product where by removing a small molecule. Sometimes it could be a water molecule. Sometimes it could be an ammonia molecule. Like when you are forming a peptide bond. And then when you are forming ester molecule. Sometimes you can call those as also condensation reactions. Okay. For these aldol condensation, we can perform the reaction under basic or acidic condition, but the base catalysis is the more common one. Now, example of this aldol condensation, you can see in this reaction, two molecules of acetaldehyde react with the same molecule to form 3-hydroxybutanol. So here you can see two molecules of acetaldehyde. So there are two carbons, so that's acetaldehyde. It can condense itself. Okay, so this is your acetaldehyde molecule, and then when you add the sodium hydroxide, you know there are acidic hydrogens. Remember the alpha hydrogen is more acidic. CH2 COH. So this alpha hydrogen is more acidic. So the base can remove this hydrogen and form the enolate ion, and then this can react with carbonyl group of another acetaldehyde molecule to give you this beta hydroxyaldehyde. We have learned the mechanism. Okay, I'm just reminding you what's happening over here. And then when you remove the water molecule, so you have a hydrogen here, and then the base can take up this hydrogen and then leave a water molecule, give you alpha beta unsaturated aldehyde, and when it comes up to this point, we call it as a aldol condensation. Okay, first it will do the condensation, the mixing of the two aldehyde groups, and then remove a water molecule to complete the process of condensation, alpha beta unsaturated aldehyde. Okay, all right. Okay. Now, some reactions happen when your aldehyde and the ketone both have alpha hydrogens. But sometimes we can make the reaction happen having one component having only alpha hydrogens, but the other one does not have alpha hydrogen. Okay, so the reaction between an aldehyde ketone having an alpha hydrogen, for example, here we in this acetone you have alpha hydrogen. Okay, with a carbonyl compound lacking an alpha hydrogen is called the Claisen-Schmidt condensation. Now this is an example of a Claisen-Schmidt condensation because one of your components where your acetone here you have alpha hydrogens, but this benzaldehyde, so this is the alpha carbon. Do we have any alpha hydrogens there? No, there are 4 bonds and the carbon is bonded to 4 carbons. No, 3 carbons, but one is a double bond. Correct? So this guy does not have alpha hydrogen, but the acetone does have. So when a reaction condensation happens between these two, we call it as Claisen-Schmidt condensation. Okay. So in the experiment that you guys are doing this week, you have several aromatic aldehydes. Aromatic means again containing a benzene ring, gonna react with aliphatic ketones. Aliphatic means there are no benzene rings. Okay, in the presence of a base to form aldol condensation products. And we're gonna keep our aldehyde in excess. In the presence of excess aldehyde. So this aldehyde we're going to use in excess. And then we use a limited amount of your ketone. So by doing that, each mole of this ketone can condense with 2 moles of the aldehydes. Okay, so we're going to have more of these. And then, so then which one is going to be your limiting reactant? So your limiting reactant is going to be your ketone because we're going to keep the aldehyde in excess. What's going to happen now? Now in your aldehyde, do you have any alpha hydrogens in your aldehyde? No. How about in the ketone? How many alpha hydrogens do we have in your ketone? So this is your ketone. How many alpha hydrogens are there? There are 6 alpha hydrogens. Remember, 3 here, 3 here, 6. But all 3 will not going to react because of the steric hindrance and other reaction conditions. Once you form this compound, it's going to be pretty stable, so it's not going to react further. But we know for sure that there are 2 alpha hydrogens, one on each carbon, can condense separately with the aldehyde, and then you will have the 2 aldehyde groups added on to the alpha carbon of the ketone, and your product is going to be something like this. Okay, and this is after doing the condensation, meaning you first will make the alcohol, 2 alcohols, alpha beta beta hydroxy alcohol, beta hydroxy carbonyl compound, and then you dehydrate to form alpha beta unsaturated ketone. Okay, so our reaction today excuse me, going to be similar to this. In the lab, it's possible to synthesize up to 16 different Claisen-Schmidt condensation products from the list provided that contains 4 aldehydes and 4 ketones. Now, if we were to conduct this reaction in the lab, so you guys can choose different combinations. Our whole class will not going to be doing the same one, but we can separate you guys, and then we can allow you to condense whichever aldehyde and whichever ketone you like. Okay, meaning you can choose one benzaldehyde. Let's say you choose benzaldehyde. Excuse me. Excuse me. And then you can condense it with acetone. Another one can do benzaldehyde and cyclopentanone, and benzaldehyde and cyclohexanone, benzaldehyde and 4-methylhexanone. So likewise. So then if you take one aldehyde, there are 4 ketones that you can react with. So that is 4 different products. Similarly, if you choose 4-methylbenzaldehyde, you can do that aldehyde with these 4 ketones. So likewise, 4, 4, 4, 4, there are 16 combinations of different products we could make by choosing different aldehydes and ketones. Okay. But your virtual lab will show you the condensation of benzaldehyde with cyclohexanone. So make sure to watch the video. So you're going to be looking at benzaldehyde and cyclohexanone condensation. Excuse me. Procedure, you're going to be measuring about 2 millimoles of your ketone, which is about 3 to 4 drops into a test tube, and you're going to dissolve. So these are going to be liquids, all the aldehydes and the ketone. You're going to dissolve it in 4 milliliters of 95% ethanol. We're going to be conducting this reaction in the medium of ethanol, and then you're going to add 8 millimoles of your aldehyde. Okay, remember we said that we're going to keep our aldehyde in excess. So 2 millimoles of ketone, 8 millimoles of your aldehyde. So your ketone is the one that is going to be your limiting reactant. Okay, and you add 8 millimoles, which is about 8 to 10 drops of your aldehyde, and 3 milliliters of 1 molar sodium hydroxide. We're going to be doing our condensation in a basic medium, so our base is sodium hydroxide. We're going to keep it at room temperature for 10 minutes, stirring occasionally, and then we're going to see if there is a precipitate forms at the room temperature. Some mixtures, some of these combinations, you will see immediate formation of a precipitate. And within 10 minutes, if you don't see a precipitate, it needs some help. And we give the help in terms of heat. Okay, if little or no precipitate has formed after 10 minutes, we're going to heat the reaction mixture in a boiling water bath for about 10 minutes. And when you heat it, you will see a precipitate start forming. You will see a solid separates out of the liquid. Some of these going to be white in color, some will have like a dark yellow, some would be like the cream color, some would be a bit orange. So there are different combinations because they have different chromophores. Chromophores are the ones that gives you the colorful the color. And the chromophores are basically conjugated systems. Okay. And then while you are boiling it, we want to make sure your reaction mixture is in a test tube, that it would not boil over. So you want to monitor the reaction mixture. And then after you get your precipitate, you're going to let it stand at room temperature for the precipitate to form. And then you can put it in the ice water bath. And then what you have created is your Claisen-Schmidt condensation product. And then you're going to vacuum filter it. Once you vacuum filter it, we're going to wash your precipitate while it is on the Buchner funnel and on the filter paper with about 5 milliliters of cold 4% acetic acid, and then a mixture of 4% acetic acid and 95% ethanol, followed by 5 milliliters of 95% ethanol. So this will help to get rid of any excess aldehyde or any excess ketone or any excess sodium hydroxide. So all those will be washed away with these solvents. And then you dry the crude product and measure its mass and the melting point. I believe you are not doing recrystallization. Okay, that is the experiment you're going to be doing. So please watch the video. You will see how the precipitate looks like and how to conduct the experiment. Now the pre-lab questions, why this reaction is called a condensation reaction. We talk about it, so you can write the why it is called condensation. And then draw a reaction scheme for the reaction you will conduct today. The scheme can be shown in two parts, one indicating the single addition product and another showing the double addition product. So should I do a one that you don't do, or should I do the one that you do? Which one do you think I should do? I feel like I want you to figure this out, how to do it. I'll do a different one, or do you want me to show you the one that you are particularly going to do today? Well, I would say first you try to do your own and then come and check to see what you have got is correct. So I will do the one that you're going to do today in the in your lab, which is benzaldehyde and cyclohexanone. Okay, so benzaldehyde and cyclohexanone. So benzaldehyde is this molecule. Aldehyde plus cyclohexanone. Cyclohexanone, there is no benzene ring, so you don't put this circle inside it. Okay, so cyclohexanone is this one. So which one is going to be your aldehyde? It's the benzaldehyde. Your ketone going to be cyclohexanone, which is this is a Claisen-Schmidt reaction because your aldehyde doesn't have alpha hydrogens. Now you are asked to draw a reaction scheme in two parts. So you're going to be adding sodium hydroxide. Okay. So in the first part, if one of the alpha hydrogen going to react, what is the product that you're going to form? So you don't have to show the mechanism over here. Okay, so you only show the reaction scheme. So what's basically going to happen is the hydrogen that I have drawn on the ketone will be removed by sodium hydroxide and form the carbon ion, enolate ion. That's going to go, I will just draw what I'm talking about. So this hydrogen will be lost and this carbon going to go and attack this carbonyl group. So your first product that you're going to be making is going to be something like this. So you have your benzene ring. Okay, and then this would become an OH group. And then this is going to be the carbon from your cyclohexanone. It's just a single bond, okay? Like this. Okay, and then what's going to happen next? What's going to happen next is this is the first product, okay? And then you have another alpha hydrogen. So you are still in your basic medium, sodium hydroxide, okay? And then this hydrogen will be lost by the sodium hydroxide, since that's alpha carbon carrying the alpha hydrogen forms the enolate, and that carbon going to react with another molecule of benzaldehyde. Now I need to draw another benzaldehyde molecule over here plus another benzaldehyde. With sodium hydroxide, you will form this molecule. OH this is your reaction scheme. And then what's going to happen? Condensation is you lost water molecule. In fact, you're going to lose two water molecules, right? To give you the condensation product. So that would be running out of space. Double bond. Well, I will draw the product in the next question. since I don't have space over here. Let's see, I'm going to draw it over here. You get the idea, okay? So it's going to be something like that. Double bond. So that's going to be your alpha beta unsaturated product, okay, after you remove two water molecules. What will be an indication that product has formed in this reaction? What were we looking at? What do you think? We talk about it when we were talking about the procedure. It is the formation of the precipitate, correct? Yeah, so that is the indication, formation of the precipitate. Okay. Determine the theoretical yield and percent yield for the reaction. In your virtual lab, you should be given the actual yield. So you can find out the percent yield. How do you find out the percent yield? Now this is your reaction scheme. How many millimoles of your ketone did you use? For your ketone, you use 2 millimoles. And your aldehyde, you use 8 millimoles. Which one is going to be your limiting reactant? It is your ketone, 2 millimoles. So, if you use 2 millimoles of that and 8 millimoles of your aldehyde, how many millimoles of your product would you be forming? Which one is the limiting reactant? Limiting reactant is the ketone. So if you start with 1 millimole, you will get 1 millimole of your product. So if you started with 2 millimoles, you will get 2 millimoles of your product. Correct? So 2 millimoles of this. Now you have to calculate the molar mass, which you have to do. Okay, it is not given in this handout. So calculate the molar mass. You can count the number of carbons, number of hydrogen, and number of oxygens. We have only one oxygen. Okay, and then you can find out the theoretical yield, which you know how to do since we have done so many of these already. So you can find out the theoretical yield and the percent yield. And then draw a reaction mechanism to explain the formation of the double addition product, meaning you have to do the mechanism for this reaction, which also I believe you can do it. Or do you want me to show it to you? Or just leave it to you to do it? Don't show it? Okay, thank you. Show it? Okay, then let's do it. Okay, so we have, I love drawing mechanisms. All right, so your aldehyde and then you have your ketone. And then you have your alpha hydrogen over there. And then we have OH hydroxide. Okay. We're going to be doing this in the presence of sodium hydroxide and ethanol. So the OH group grab the hydrogen and give the electrons in this bond to this carbon. So that will make this guy negatively charged. Okay, and then this is this can participate in resonance like that. So this will give you this guy. O minus enolate. So this is your enolate, right? Not pretty. That's the enolate. Okay, then what's going to happen? And now you have your benzaldehyde. your benzaldehyde right there. So the flow of electron takes place like that, and it's going to go through this carbon and then open up the pi bond, and then that will give you this reaction where you have O minus like this, correct? And then we are in sodium hydroxide medium, and then OH minus plus hydrogen, you generate a water molecule. Okay, remember, water molecule. So this enolate ion go and grab hydrogen from a water molecule, giving you the alcohol. OH. Okay. And then the next part, you have another alpha hydrogen right there. So the same thing happens. The same thing repeats. Hydroxide ion goes and grab this hydrogen, give its electron to this carbon to form a carbon ion, enolate ion. Okay, enolate ion, that gives you this product, benzene ring, OH, O minus. So this can participate in enolate ion formation. O minus, so this is the enolate, and now this is going to react with another molecule of benzaldehyde. So okay, this will give you when you draw these things on the paper, you should be able to draw it more nicer. Okay, so we will get this product. Oh, I forgot to put the benzene ring, OH. Now we have beta hydroxy ketone as the product. Now what's the next step going to be? Removal of the water, dehydration. Okay, how does the dehydration takes place? Remember, you have a hydrogen here, you have another hydrogen over here. So the base, OH minus, with its lone pairs, 3 lone pairs. So the hydroxide group goes and grab the hydrogen, gives its electrons to form a pi bond, and then lose OH. Same thing happened with the other one also. Okay, same process. I'm gonna come and take this hydrogen, and then you have your completed product. Alpha beta unsaturated carbonyl compound, which is your Claisen-Schmidt product. Like I said, Draw these molecules more nicer, more straight bonds when you are drawing it on the paper. Okay, this is the best I can do with my iPad writing. Okay, great. So that is the mechanism. Okay. All right. If the ketone was changed to 2-butanone and the base was changed to LDA, what would be the structure of the single addition product? Now the ketone was changed to 2-butanone. So here our ketone is cyclohexanone. What about if you have 2-butanone? So what is 2-butanone? 2-butanone is 4 carbons, and on the second carbon you have a ketone. And LDA is the base that you're going to use. And this is going to react with your aldehyde, which is the same aldehyde, benzaldehyde. LDA, remember LDA is lithium diisopropyl amide, which is a pretty strong base, and at the same time it's a bulky base. So this is where we have our alpha hydrogens, right? There are 3 alpha hydrogens and 2 on here. So LDA being a bulky base, which hydrogen do you think it is more easily approach? Which hydrogen? Is it going to be this hydrogen or this one? A or B? Least sterically hindered one is hydrogen A, right? So the LDA, lithium diisopropyl amide, the base, will grab this hydrogen and form the enolate ion on that alpha carbon. Okay? So then what would be the structure of the single addition product? Meaning, so you will form, LDA will come and take this hydrogen and then form enolate there, here, and it can form the enolate ion and this is going to then react with your benzaldehyde. And this carbon then will go and react with this to form minus. And then this will grab the hydrogen to form OH group. This will take a hydrogen lithium diisopropyl. LDA will be protonated now. Remember the hydrogen, LDA from here take that hydrogen. So oxygen will take that hydrogen back. Okay, and then will become protonated. And then if you lose a water molecule through condensation, you will have this product. There's no bond right there. That would be the product, single addition product. Okay. Okay then. That's it. Talk to you later. Bye-bye.